All right, example A asks us to determine if the given figure has rotational symmetry, and then to find the angle of symmetry and how many times it can be rotated. So first of all, if we take a look at this figure, in fact, let's grab it separately here. I'm going to have to, there we go. If we grab it like this, there we go. If we grab it separately, we can see that we can rotate the figure around that center point. And as we rotate it, the figure stays virtually the same. And you can't really tell without looking at my outside bounding box how that thing's been rotated from where it started. So yes, it does indeed have rotational symmetry. The question then is how many times it can be rotated. So if we call this side here, let's mark it, call this side 1. I need to be on top of it. Oh, we can do that. We'll call this side 1, 2, 3, 4, 5. So we have 5 vertices. Now if we were to take that thing and rotate it, right now we have our first location. We could rotate it so 2 was up, so that's 1 rotation. So that's our, we have our first location, then we can rotate it once, we can rotate it twice, 3 times, 4 times, and then 5 times back to where we started. So there are 5 possible places of rotation where we can evidence rotational symmetry. So we have 5 points of symmetry, or 5 rotations. So to find out what the angle is, then we take the full rotation, which is 360 degrees, and we divide it by 5. 360 divided by 5 is what, 72? 72 degrees. So 72 degrees is our angle, and then 5 is the number of times it can be rotated to demonstrate rotational symmetry. Yeah? All right, example B gives us a little letter n and has the same question. Determine if the figure has rotational symmetry and then find the angle and how many times it can be rotated. So if we grab the n, like so, we can see that for most of the way around, it does not have rotational symmetry. But if we go all the way upside down, like so, it does. So this figure then has, it can be either right side up or upside down. It does have rotational symmetry. So yes, it does have rotational symmetry. But the angle then is just going to be based on the number of times it can be rotated, which is 2 times. And we figure out that angle, 360 divided by 2, gives us 180. So it has a 180 degree angle of rotational symmetry. And we only get 2 rotations to actually meet that rotational symmetry requirement. Okay? And then finally, example C. Example C gives us a checkerboard and has the same question. So first of all, does it have rotational symmetry? Well, if we rotate the checkerboard, in fact, let's do what we did before. Let's number our sides here. 1, 2, 3, 4. Good. And now if we rotate it, yeah, we can see that it does indeed look the same every time we go around a quarter of a turn. So we have 4 rotations, which means, yes, it does have rotational symmetry. It has 4 rotations. And then to find the angle, we take 360 divided by 4, which gives us 90 degrees. So it has a 90 degree angle of rotational symmetry. And we're done.